Hello, my friends, data scientists, and those pursuing to master the data science. Today's lesson, I'm going to show you a complete treatment of the linear multiple regression analysis. It will include checking of the normality. It will include detecting heteroscedasticity. That means the variance has to be homoscedastic. And it will also include the tests for normality, including Shapiro-Wilk p-test, p-values, Shapiro-Wilk statistics, and it will also include the multicollinearity problem tests. So let's start for that. I already have these libraries imported: Pandas, NumPy, SciPy, Statsmodels, Plotly for interactive visualization, Matplotlib, and I have already models specified. The model is sales revenue equals some intercept term plus slope of customer base minus slope of interest rate plus slope of TV ad. TV ad is a dummy variable with 0 means not present and 1 means present, TV ad present. So what is the impact of having a TV ad? That is the intention of the purpose. So here I have data generation completely through randomization. There is no endogeneity problem in this. All the variables are stochastic. So the observations are 60. And I have specified the data frame as this: sales in millions, which is intercept term as 10 million, plus customer base increases by 0.05 times the customer base, minus 0.5 times the interest rate, plus 2 times TV ad, plus NP random normal 0.6n tries to capture the noise, the unexplained, the disturbance terms. Okay, customer base 200,000, interest rate and TV ad. Interest rate ranges from 10% to 25%. Okay, so with that data, I have 5 columns here, including the index, where I have sales, customer base, interest rate, and TV ad as a dummy variable. So the first thing in this data to do is let's examine the scatter plot. Let's examine the residual scatter plots. Let's examine whether there is a heteroscedasticity in the residual distributions. If the residuals are distributed scattered way, there is no pattern of residuals, then we can say that the problem of heteroscedasticity is minimal. Okay, for that, let's start with residual plot observation. Residual plot display. Okay, we're going to start with that. So for that, I'm going to use the Plotly from Plotly that subplots, import plot maker, make subplots. Okay, that is the library we're going to use. Fig equals make subplots. Here we're going to define rows equals 1, comma, calls equals 3. We will have 3 columns plus subplot titles equals, here we're going to show the title of each of these plots. There will be 3 plots. So first is going to be customer base versus sales. Okay, customer base versus sales, comma. Second is going to be interest rate versus sales, comma, after the quote, comma, TV ad versus sales. Okay, those will be the titles of those 3 plots. Now let's go ahead and start with the plots. Fig.add scatter, add scatter X equals df. So what scatter are we going to do? We're going to start with customer base. These names have to come exactly matching with the data frame names. Okay, so percent thousands, scatter base. Okay, customer base X equals customer base, comma Y equals, what is that going to be? Obviously the sales, right? Sales in millions. Okay, so that is the first scatter, comma, let me, comma, mode equals marker, mode equals markers, comma, name, let's give the name to the plot. Did I give the name in the first one? Oh no, TV ad sales. Okay, this is, yeah, name equals, because this is the first customer base. Okay, customer base, row 1, column 1. Okay, this is going to be, comma, row equals 1, comma, col equals 1. Okay, this is one plot. Let's go ahead and fig.add scatter. The next one is going to be X equals df. This is going to be interest rate, right? Interest rate percent, comma, the rest is going to be the same. Y equals df, quote, sales in millions, close, and again mode equals markers, comma, name equals interest rate, comma, row equals 1, comma, col equals 2. Okay, this is going to be column number 2. And the last column, let's do this. Col is going to be 3. Name is going to be TV ad, mode markers, sales millions. This is going to be TV ad. Okay, so we sketched the 3 plots. Now we need to put the labels and make them lively. Okay, so for that, fig.update, update axis, axes, which axis? X-axis, title text equals customer base in thousands. Okay, customer base in 1,000. Row equals 1, comma, col equals 1. So 2 more for that. Okay, here is going to be update x-axis, not customer base. It is this time going to be interest rate. Percent. Column is going to be 2. Okay, the last column. Here, column is going to be 3. 3. Instead of interest rate is going to be TV ad 001. Okay, that sets the labels of that. Okay, now let's fix the Y label. Fig.update y-axis. Okay, same syntax. Title title text equals in the quotes sales in millions, row 1, comma, row equals 1, comma, all equals 1. Okay, so we updated the y-axis as well. Now let's show fig that so. Okay, so if there were not much errors, this should be I should be able to show this clearly here. Shift enter. Okay, df is not defined. Okay, when that happens, we just have to run the kernel again. Start again. Running. So the error was a typo. It says RPW should be row, ROW. So now if there is no more typos, it should be showing me the plots. Okay, here you can see I have 3 plots. Now you can see clearly there is no heterogeneity problem, heteroscedasticity problem. Okay, because the dots are distributed, scattered. There is no pattern. If say we have a trend line here, fitted line here, if you look dot above the line and below the line, if you compute their sum, it will sum to 0. Expected value of EI equals 0 proves this. There is no pattern in the distribution of residuals. So we have achieved the property of homogeneity, homoscedasticity, equal variance of the predictors. Okay, so once we have completed that part, let's go ahead and try with the part of, let's run the regression. Okay, so we have checked the property of equal variance of the residuals. Now let's run the regression, which we do like this: multiple linear regression. Okay, now reg equals smf.ols formula, which we have from Statsmodels, we imported that formula, equals q. We are doing q. This is parsing issue because of the Python. The columns have the strings, columns have the brackets 000%, etc. It creates parsing issue. To correct that, we use q. Q is called patsy correction. Okay, q, and here first is going to be sales in millions. Let's close it and close here. Now we put tilde because tilde connects the dependent variable, response variable, with the independent variables, the predictors. Okay, tilde. Now let's go ahead with q because we have all the variables like that. Q here is going to be interest rate percent. Close it. Interest rate percent. Let me close that. And plus, what is the next? Customer base, right? Q customer base in thousands. Let's close that. Plus, what is the other? TV ad, right? Q TV ad. Okay, TV ad. Close the quote. Okay, comma. Data equals df. Close it. Close the OLS function. Dot it. Okay, so fit model. Now let's print and see. Print reg dot summary method. Okay, all right, so Let's pray that there is no typos and other syntax errors. So enter. Yay! There is no typo and other errors. Now you can see the results. You can see the regression results. Okay, look. The explanatory power of the model is 0.671, which is pretty high. Even if adjusted, R-squared is 0.653. F statistics is pretty high. And looking at the probability values, you can clearly see that customer base is significant at 5% level, and the others are not significant at 5% level. Regarding the interpretation of the coefficients, we can say that the sales intercepts the y-axis at 7.57 million, or rounding up 7.6 million. At that point, the sales intercept the y-axis. And the other coefficients, sign-wise, they are correct, because higher the interest rate, lower will be the available money for borrowing money, because at higher interest rate, you cannot borrow much. Lower will be the available money. As a result, the sales will also decrease. You can see in practical life, many retail stores and others are issuing the credit cards, extending the sales for the purpose of increasing the sales. This is because of that. So the sign is correct here. Even though it is not significant at 5% level, it is significant at about 15% level. And customer base is significant. And what we can say is, for every 100,000 increase in customer base, there will be an increase of $467,000 sale. Similarly, TV ad is not significant, but the coefficient says that for the presence, if the TV ad is present, then the sales will increase by 1.9 million. If no TV ad, then there is no 1.9 million increase in sales. Okay, so that is what we can say. And we can look at the conditional number here, and which shows that the conditional number is really high, 3003. Any number above 100 in conditional number shows that there is a serious problem of multicollinearity. Multicollinearity suppresses the precision of, increases the standard errors and suppresses the precision acceptance of probability. Okay, so multicollinearity appears by that, and we will check that with the following example. Okay, so again, to see if the residuals are normally distributed, if there is a normality or not, we have some diagnostic tools which are running like this. Let me run those diagnostic tools. I am going to use in that two things. I am going to use QQ plot and histograms of the residuals. Okay, and then numerically also through Shapiro-Wilk statistics, I am going to show whether to what extent we have the problem of residuals not being normally distributed. Okay, so let's start with that. Fig, I want to run side by side histogram as well QQ plot. Okay, that's why I'm creating AX2, AX1, comma AX2, two plots side by side, equals PLT dot subplots, PLT dot subplots. Okay, subplots will be 1, 2. We'll have two subplots. Fig size, I want to control the size of the figure, equals 12 and 5. 12 wide, 5 high. Okay, now begin with QQ plot, let's do this. Stat dot prob plot. So what we're going to need, reg dot recid, comma dist equals norm. Okay, comma plot equals AX1. Okay, now let's set the title also. AX one dot set title. Set title. What is going to be the title? Title will be Q dash Q plot for residuals. Okay. Let me just check if I did not make error. PLT dot show. If I have not made syntax error, the QQ plot will show. Shift enter. Yes. See here, we can say from here that the residuals are normally distributed because they are clustered along the diagonal of this. So now let's fill for the histograms. Okay, histogram ax2 dot hist reg residuals reg resid. Okay, reg that resid. We're going to draw the histogram of the residuals, right? So bins equals 20. Let's draw the 20 bins. Color equals steel blue, comma, edge color equals black, comma, edge color equals black, comma, equals black, comma, alpha equals 0.6. Okay, that's one. ax2 dot axh line. I want to draw the horizontal line to show it differently. 0, comma, color red equals red, comma, line style equals dash, line width equals 2. Okay, line width equals 2. ax2 dot set x label, what is going to be in the x label? Residuals. Okay, similarly ax2 dot set y label, what is going to be in there? Frequency. Okay, x label, y label, plt dot tight layout, plt dot show. So this should show the plot histograms as well. Shift enter. You see, now you can see this histogram well shaped. So ax line, I have something, it should be vertical line to show the mean 0, right? To show the mean, it should be vertical line. Okay, now you will see the vertical line, red dots here. You see here? So from here, we can see clearly that the residuals are distributed normally because they are along the horizontal line, as well as the histogram is approximately bell-shaped. To check this in the numerical fashion, check this numerically, let's use Shapiro-Wilk test for residual normality. Okay, for that, Shapiro-Wilk test for residual normality. Okay, that test is very handy, a short one-liner, but very useful. Quantitatively, it gives you the numbers. Okay, so stat, comma, p-value equals stats Shapiro. So what is that? Reg dot resid residuals. Okay, now let's print it. Print. Let me put the f string /n in the new line. Shapiro Shapiro-Wilk test stat. Okay. Statistic test stat STIC equals, no, not that, equals stat 4 decimal places. Okay. 4 decimal places, comma, p-value. P-value equals p-value, also 4 decimal places. And close that. Okay, now I would like to put some interpretation here. For that, print f interpretation. How do we interpret that? Here, p-value greater than 0.05 means residuals are normally distributed. Okay, and stat, Shapiro-Wilk stat around stat close to one mean the same. That is, residuals are normally distributed. Okay, that is the quick small test, and let's run it and cross the finger that there is no syntax error. Yes, no syntax. So Shapiro-Wilk test statistics gave us 0.9923, so which is very close to 1. P-value 0.9706. Oh, much bigger than 0.05. That means the residuals are normally distributed pictorially as well as in numbers. We can see this. So the last item I want to show you today is, as I said before, we are suffering from multicollinearity problems. Let's see which variables are suffering from that. So for multicollinearity, check with VIF. Okay. So for that, X equals df. Let's summon all the predictor variables. Customer base 000, comma, interest rate percent, comma, PV add. Okay, those were the 3 predictors, because we check multicollinearity among the predictors. Okay, and VIF data equals PD dot data frame data frame. We're going to define inside here variable variable is x dot columns, comma VIF value. Oh, let me bring it here. VIF value equals list comprehension variance, variance inflation factor, x dot values, comma, I for I in range x dot shape. We are summoning column because column is axis 1. Okay, so for I in column x dot shape, let's print VIF data. Okay, So let me write the interpretation as well. Print f. Now let me just write docstring 1, 2, 3 f VIF less than 5 indicates low multicollinearity, and VIF greater than 10 indicates high multicollinearity. Okay, so that being the standard, let's check it and see if what values we get of all of the 3 predictors. Hopefully there is no syntax error and we'll get the results. Yes, we got the results. So here we can say, you see custom base has VIF value of 6.30, so which is higher than 5 but less than 10, so it's not really high multicollinearity. Similarly, interest rate has 7.21, also the same, less than 10, so not really high multicollinearity. And none of the only value that has less than 5 VIF is TVAT. So we can conclude that the model is pretty good in explaining the sales and helping the company to decide on the basis of these factors, macroeconomic factors, as well as business, the customer base, the market, the business can start more outlets, can expand their outlets. Sales will increase because these are the factors. So that's all we can say from this regression analysis. This is a complete analysis of linear multiple regression, where the important factors are included in explaining the variation in response variable due to the predictor variables. The predictor variables have captured much more that is needed for increasing the sales, to attaining the sales. The model has explained 67% of the variations in response variable, which is sales, by these predictor variables. So there is some factors that are not captured by the models, which are 0.33%, less than that. So this is all I wanted to say to you and explain to you, show you the power of Pandas, NumPy, Python, included with statistical analysis. So this is the place where you will learn about econometrics, statistics, and all these methods using Python. So please subscribe to my channel. Stay tuned. Thank you for watching. Thank you for listening. Stay tuned. Subscribe to my channel, where I will explain you much more, show you much more statistics, statistical analysis, data science with more clarity, and with tutorials with more apps and applications. For now, thank you. Appreciate your attention. Please subscribe to my channel. Thank you. Bye-bye.